machine is actually supposed to retrieve a cup. Cap, I forgot to put it, so I'll put it once it placed it. So that's the cap station that I will tell you about in a bit. Okay, I broke it.
This is human error.
So now the machine has covered a cap, and during the game that would be essentially pre-mounting something on a machine, like a piece you were to mount on another piece later on. So that's what this represents. And now the robot needs to pick up the empty good. In the real game, it would displace it somewhere else and would get a new work piece, but here we just continue with the same work piece. And then we drive to the other side, mount it again, and so it's doing it over and over in this kind of demo. The tricky part here from the robotics side is that the tolerance in both directions is about 2 millimeters. That took some doing to get this with sensors which have precision in about that size and that range. So yeah, that took about a year to get. So I think that's it for the demo for today, for now, and then we can later on during the coffee break do it again, and then you can have a closer look.
So what we're going to do now is Tim is going to explain what it is he just saw, and then I'll speak for a bit about planning and execution, and then we'll get to the hands-on session. So we're going to hand you flash drives that you can boot from, and then you can run a simulation of the full playing field of this. And we're going to show you some robots moving around in the simulation and how you can execute actions, and basically we'll follow the schedule.
Yeah. So, and then after the coffee break, there we will focus in particular on the planning and execution system. Before that, we will focus on what's already there for the simulation, and then the full second round will be focused. So, if you have the planner from yesterday, that's all news. But so here are the two perspectives that we're trying to combine in a way. The planning perspective is that, well, I define my initial state and my goal state, and then out there come actions, and I just do them. From the robotics perspective, there's a lot more things involved, like perception, motion planning, trajectory generation for the arm, and then creating the planning problem is merely a hindrance on the way to the demo to present what you actually did as a roboticist. And it just takes time. So we try to bring this closer together, and we actually allow the robotics community and the planning community to work together on this particular problem. And then from the planning perspective, there's also the idea to build up the knowledge that's required to actually tackle robotic scenarios, deal with their platforms and decision architectures, and see what's going on. So that is the game from which the competition you're proposing is inspired. That's the RoboCup Logistics League. That's a photo from the competition last year in China. The next competition is coming up in Leipzig in about 2 weeks. The overall field, so the overall task that we have to do, maybe I show it here, is that here are these stations, of which you see one here. They have different types, and they can do different steps on the workpieces. And now the group of robots, which are 3 robots per team, have to coordinate on which robot is doing what at what time. And by that, they refine a workpiece step by step so that they get a final product that they can eventually deliver. And you also see that there are 2 teams here at the same time playing in the field. That's not so much meant as an adversarial scenario, but more to increase uncertainty. Because now, if I go to the map, you see that the machines are assigned to one specific team, and the teams in RoboCup are traditionally named cyan and magenta. So you see that for one team, the machines are distributed over the whole field. And that means that you have to pass by other robots of the other team. And that increases uncertainty in terms of travel time, and requires a little bit more doing to get optimal path, even in the presence of other agents that move without you knowing how they work before you do it. To ensure some fairness, just there's this middle axis across which we mirror the game. So that's just for the competition.
Are the little robots allowed to try to trip the robots from the other team?
No, so pushing is strictly disallowed. So robots get punished for that by being taken out of the game. You may restart a robot once. So, and as a restart also counts if it fails on its own if you want to pick it up. So it's a high risk, and you really try to work it. It's also not allowed to sit in front of the machine of the opponent team, for example, so that they actually cannot perform the production steps. But we've also tried this in simulation, and it turns out that it's actually worse for your own performance trying to beat back the other team. So you better just focus on doing your own job. Okay, so these are the machines in a little more detail. They're from the German company Festo. They're also producing the robot, and they're sponsoring the competition. And I should have mentioned at the very beginning, we're also very grateful because they're also sponsoring this tutorial by providing us with a machine and covering all the cost of bringing everything here, and ordering us the USB sticks for the tutorial later on. So they actually sell this for mechatronics education, and there the idea is you would take a couple of those machines and put them side by side to get the production shape, the classic production shape. And now they want to see how they can actually do that in this larger context of smart factories and Industry 4.0, how this can be done with a mobile robot. And that's where these very narrow tolerances come from, because they actually think that the machines are static once they're set. There are 4 types of machines. One is the base station, so these are the workpieces. And from the base station you can get these basic elements in 3 different colors. Then there's a ring station, which we don't have here, but it looks similar to this, but it has 2 of these things. And each ring station has 2 different ring colors. And then there's the cap station, of which team has 2. This is exactly the station that we have here, that can buffer and mount these caps on top of the products. So I essentially now already told you how the products look like, but I will go into more detail soon. And then we have the delivery station. That's just a station that has 3 different slides. It's like the gates at the factory in the end, and you need to decide on which truck we load. So one team has 6 machines, 12 machines in total for both teams. And that's what the robot looks like in a little more detail, so you can also later come and look. So this is essentially the base that you buy from Festo as is, together with the tower and the table. So that's the base platform that so far every team that competition has to use. All the sensors and the extra laptop on top for more computing power, that's what the teams can add extra if they want to. So within certain limits, you're free to add what you like. So there's this extra gripper. You're always only allowed to carry a single workpiece. You cannot just buffer a few and then drive around, so you can only carry one. There are many cameras. One is to recognize markers. So each machine has this marker here that uniquely identifies the machine and the side of the machine. So we have a camera here to recognize the markers. You have another camera here to recognize the light signal. There's another camera here which we use to recognize the conveyor belt, but we've just switched to a 3D sensor for higher precision. There's Wi-Fi on board, but Wi-Fi at RoboCup is flaky, and you will notice in the simulation, and we also simulate that. We actually give you good Wi-Fi in terms of RoboCup, that is 10% packet loss. If we want later on during the discussion, this can be turned off or be increased depending on what the demand is. Okay. So the overall game is controlled by something that we call the referee box. It's an autonomous agent on its own. The sensor data that it gets is all the data it reads off of the machines, and based on the specification of the game, it will produce the proper feedback on the machine. So for example, the machine taking the workpiece and retrieving the cap, that's all decided by the referee box. That's why the extra laptop is put there. So all the control is done there, and this is merely an execution unit. We use the very same later on during the simulation. So that means that the agency that we provide in the real world and in the simulation is the same. Up to a very high fidelity. So we also have our domain designers separate often from the rest of the team, and only a few weeks before the tournament we put them together. It usually works. We also use this for recording a lot of information. So for example, each and every message that gets sent is recorded, and we have used that data, for example, for in-depth evaluation of the games, and got some interesting insights of why the team performed better. The game is split in 2 phases. I won't go into detail about the exploration phase because that's not what we intend to do here. So in the production phase, you get orders, I will specify what it is in a second. One like here, deliver one product which has a red base, a yellow and a green ring, and a gray cap in a certain time window and deliver it to gate 3. And then it's up to the team to decide whether they're going to pursue this order and what resources they assign to do this order. Yeah, so that's all I want to say. So that's how the production process actually looks. So here are the different complexities of products depending on the number of rings. Each ring obviously increases the risk of mishandling a workpiece. And essentially, if you drop a workpiece or otherwise can't use it anymore, there's no way to recover it. You lose a lot of time and effort that you put into this one workpiece and product. The production chain up here is an example for the most complex product. The blue boxes here represent machines. So by now you can guess that this is the base station, ring station, and the cap station. So at the beginning of the production phase, the teams get told which ring station produces which ring color, but not, so there are 2 ring stations and they have both, so there are 4 different colors and the 2 ring stations each have 2. So that determines which resource you need to block to get a particular color ring. Some rings have the additional constraint that they need additional material. Think about a painting machine and that additional material is filling in the paint in that machine. So this is denoted here by these all-color bases. Essentially, you can just get any base and throw it in there, and it's just a number that needs to be pre-filled. So that means now we get a red base from the base station, mount a yellow ring which doesn't need additional material. For the orange ring, we need to bring 2 additional material, and that's actually rather expensive to bring 2 additional material because it needs a lot of traveling of the robots on the field. And then the green ring needs another extra base element. Here we have the cap station, and this here what the cap now knows that you need to buffer the cap first, so that's another step that you need to do for the production chain, and then you actually get the final product, and then you have to deliver it. So a product, as I said, has 4 complexities. There are 3 different kinds of base colors, 4 ring colors, 2 cap colors. You have a lead time for each order of a few minutes, and depending on the complexity, that's for simple complexities it's shorter, and for higher complexities it's obviously longer. So that you have a chance to actually produce. But especially for the higher complexity goods, there can be virtually no opportunistic encryption because there are about 250 different variants, and it's hard to guess which one will come up later in the game. So it's an important part. The orders are posted dynamically at runtime with the appropriate lead time. You're not told about all the orders at the beginning of the game. And there's we talked about the certain time windows in the slide before. So that's an example of how these production steps would fit together, and that's for the most simple product. So we have here the product which has a black base and a gray cap, and the goal and the task is then go to the base station, get the black base, go to the cap station, mount the cap, and then deliver. So the first thing that we usually do is just pre-fill the cap station, because that's an easy task you can do. And here I will assume that this is all done by a single robot. So first we go to the shelf on the cap station, grab a base of the pre-mounted cap. It's just a carrier container, the base, so to speak. We go to the input side and deliver this. The cap station retrieves the cap. Then we need to go around the cap station again and dispose of this now empty base. And for the sake of the example, we accept this is a messy robot and it just drops it or something. During the game, you would not do that because it's actually too costly. So then we can go to the base station and get the actual workpiece that we're interested in. Fill this in on the input side. Need to go around and retrieve it again, and now that is the final product that we retrieve, and only then we can deliver. What I didn't mention so far is that also in the context of smart factories, there's always communication involved. So here, every time if there is prepare a machine for something, that's actually active communication that the robot has to do with that machine through the referee box. So each machine has multiple things it can do. The ring station can offer one of 2 ring colors, the cap station can either retrieve or buffer. The base station has 3 colors that you can choose from, and the delivery station needs to be told which gate you want to deliver to, so that you need to incorporate into your plan. So you see that already here we have many fragile points, so essentially each time you approach a machine and move off, that's a fragile point where things can break, especially if there's low tolerances. And there's already potential for cooperation. In the simplest case, that would be that one robot prefills the base station while the cap station, while the second robot already retrieves the base from the base station. So that the least you can do, and maybe you could do even better. Especially if you have a close deadline that you need to deliver to, you could already assign a robot to pick it up while the others just bring it to the machine. So just to give you an idea how this is rated, there is a scoring scheme, and so that's the one that we are going to use this year during RoboCup. So for filling an additional base, even though it's actually an expensive operation, you only get a few points. That's how the PC decided. For the higher complexity productions or processing, you get also some points. So this is actually if you mount a ring which needed additional material, you get awarded afterwards once you mounted the ring through these 3 lines of points. Then we have points for the final step. So essentially that's a risk-based reward. So for the simplest product you only get 10 points, but it goes up to 80 points for the highest complexity product. So if you mount the 3rd ring on a 3-ring product, you actually, that's almost a match winner at the moment. So, just to give you an idea of how hard, so we introduced these physical processing machines only last year, and teams had a hard time adjusting, so there was only a single team during the whole competition being able to deliver the simplest complexity product once. So that's how hard it was at the beginning just to get the handling of the machines right. And then for the delivery you get points, what's not funny, you even get points for slightly late delivery, but that's not much interest. So delivering then also is very good points. And it used to be that you only get the points on final so the points would accumulate for a product, but you only get it if you make the delivery in the time window. And this has been relaxed this year, so the points here for the higher complexity productions are already awarded once you do them. So there's a little cheat that you can do that you're not aiming for final delivery, but only for doing these higher complexity goods. And we have to see how that works out this year. So we've so far talked about the RoboCup Logistics League and how this is done there. And based on the scenario that we presented last year, we came to the idea to make a planning competition out of this, especially, or in particular to bridge this gap between planning and robotics and have one accessible scenario. So I've done a couple of other robot scenarios before, and it's really one of the simpler ones. So, but it's still interesting enough, and with the focus on the logistics, it poses an interesting planning problem, so I was told. So we hope that you all will be interested and some of you participate next year. Especially this, so currently what we're mostly doing is doing, is that actually the next slide? Yeah. So let me talk about what's currently the best performing system out there. So that's a rule-based system that classifies certain situations during the game. From whenever the robot is idle, he chooses what he can do next, which has the highest reward regarding the game. The reward at the moment being a hard-coded prioritization of the tasks that we can do. And there, if we, for example, want robots to cooperate, we need to encode this explicitly. So we need to encode that robots need to wait for each other and to communicate, and that's rather cumbersome. And also the window of opportunity when robots can actually cooperate is rather narrow if you do not plan for it in advance. So that's one of the things that we also hope to get out with 2 projects we're currently doing with a centralized planner, because there you have all the information available and you can actually time these things a little better. So that is the simulation that we envision for the start to be used. And that's also the simulation that you will be using during the tutorial. It's based on Gazebo, which is one of the most widely used robotic simulators out there. For example, known from the Dark Robotics Challenge in the recent years. As I said, it's rather close to the actual thing. So the models that we have here for the stations are based on actual models that Fester is using themselves. So they're rather accurate. And then the reactions, since they're all programmed or coming from the referee box, are really the same as the real machines. And as I said before, that we actually can split this high-level development and low-level development rather easily with this simulation. This simulation was developed by our team in Aachen, and then parts of it were also developed at TUM in Munich from another RoboCup team. And it has also been the basis, for example, for common with this one. So that's how the architecture looks like of that simulation. So the environment agencies provide with the referee box, as I said, there's obviously a visualization. And then there are the models and the plugins inside that you don't have to worry about, essentially. But what it means is that there's this one node or one system per robot on the side that interfaces with the simulation. And essentially, if we later get to the planning system, that's sitting even somewhere to the side here, interfacing to the simulation through one of these middlewares. So for the system integration, we're using two systems here. One is the Fox Robot Software Framework that we have developed in Aachen. That's the basic layer that grabs the immediate simulation. And then there's a full ROS wrapper and integration available so that people are used to ROS or knowing ROS can fully interface with the simulation front end. So depending on how close you want to get and what your favorite system is, you can choose. So that's how, or one idea how the overall architecture for this system could look like. I'm in particular showing this with regard to the different kinds of tracks we have envisioned so far and for which we hope to get feedback from. So on the top we have this task level planning executive, which takes into the main model to generate a plan, which is then handed over to the execution system, and based on what the current state is, it determines whether the plan remains feasible and then executes it or adapts it. Below this are the robot software frameworks that I just spoke about. In particular, here is one thing which we call the behaviors and skills. These are the basic behaviors that, for example, perform the machine handling. And they're encapsulated in about a dozen relevant actions that you can do. And these will be provided as a start. Then there's the simulation. And as you see, the only interaction with the simulation is through that, through one of the software frameworks. And then the referee box is what's providing essentially the goals for the planning system, so the orders that are posted, and what provides the agency to the simulation environment. So these are the tracks that we have envisioned so far. But they're explicit, so that's where we would like to have your feedback later on. And just, oh, there's actually rain spraying. Can we close the window?
Don't know how.
Is that fully? Other one. It's like spring. On top.
Go see if there's someone who knows.
Not just on the robot. Hey, Dan. Hey, Dan. At the very least, you could close.
Yeah, maybe you can just close the lids.
Yeah. Let Michael go. Makes the lines close as well.
Okay, it's not an outdoor robot. the 3 tracks we have in mind so far. First is that based on this image, anything that's within the gray box or touching the gray box, so the main model, state estimation, task planning, and execution monitoring, that could be extended or replaced by entities. The second one would go a little bit into the robot software stack, so allowing to change behaviors to replace.
Is that good enough?
Yeah, I think. Thanks. To replace the behaviors or even the execution engine of the behaviors for the path planning. Path planning here, or motion planning, is interesting because it can make sense to do cooperative task planning or actually do reservations or something so that at least the robots in your own team try to avoid each other. And then the third would be freestyle. That could also, so you could replace anything but the simulation and referee box. So essentially interface with anything on the outside. That could also be interesting, for example, to get people from the robotics side more interested, because usually roboticists tend to have their tech framework they want to use, and that could be the thing.
So,
okay.
Go questions. So on the previous slide. So what about planning alone? So there's a lot of people in the planning community who do planning, but don't do execution.
Yeah, that's true.
And you would want to be able to. I think those people might want to just say, well, the level playing field on the execution, but they want to differentiate themselves on the planning.
So, right, we could have, kind of sub-tracks of that one where, one is basically plug in your planner into the execution framework we provide and see how that works, right? One could be, we're going to provide you kind of a skeleton for an executive, and you can handle some events like, a new order or a failure or whatever. And then again, plug in your planner or do whatever you want. So there's lots and lots of different options here, which is why we want to hear feedback from everyone here about what they want to do.
In RoboCup Simulation League, what they did to make life easy for people was they created a stupid but functioning team, and then you could do any changes that you wanted, but you would always have a function existed.
Yeah.
So it might just suit to the center of the code, and if you're interested in passing. But yeah, if you do a demo that is just a minimum base, and then people can add to it, then everybody
So
can do whatever.
that is a good option.
There's kind of the system that will be on the USB stick. So there you have all the bits and pieces once in place, and then you can go from there.
Yeah, really primitive, but it works.
What's the policy of the competition as far as requiring competitors to open source their system?
No decision or no suggestion have been made so far. So judging from RoboCup, there's not a strict requirement, but some teams do it, and they usually get more credit than the others, so that's the incentive. But
is there a requirement in IPC?
Yes. IPC have to open source your data.
So that could be in there, but
For a good reason.
Yes.
I'll tell you that.
What's the team aspect? Like, is there some adversarial aspect to this?
no, this is really to increase uncertainty, for example, in terms of travel times, that you have to pass these other robots. And so otherwise you could just say, I'm taking 5 seconds from here to there, but once they're on the engine, it's more non-dependency.
I'm just wondering, is this planning or heuristic search? Like, are we talking about domain-independent stuff, or are we talking about like creating your own advantages?
That is one of the hardest questions, because this is one domain. Now, I wouldn't even know how to define, right, domain-dependent versus domain-independent thing for this one domain. So we might
have the behaviors.
Yeah, so those are all good questions, and we will discuss all of them, and we'll also send out a questionnaire to everyone to kind of, capture everybody's preferences a few days.
Two tracks, and one of them you could force everybody to use a common representation. That would be the planning track.
That's one option. There's issues with that, but yes, that is one option.
But a number of people have been involved in making this happen, and different people have different goals. Right? My involvement in it has been that there's a huge price of entry to get into robotics, right? And then you can spend all your time doing task execution. You can do controls. You can do hardware integration, and then it's harder to make advances in the theory. If you make good advances in the theory, then you can be working in the deployed world. Right? So we do have lots of domain and planning collaborations, but first, the purpose of this, in my mind, is to reduce the price of that bit so that people can work with real robots and gain insight of the robot while still kind of advance the theory.
As you might know, there is the ROS plan framework, right, which allows to use any planner and interface with ROS system.
Yeah, would essentially be here an alternative, right?
Yeah, so, I mean, because the aim of the ROS plan, now many groups are using in our community to interface with the ROS system like this one, right?
Yeah.
So how that can be used there?
Yeah.
It can.
Yeah.
So we are not strict to this kind of architecture we want to go.
No, but
okay.
ROS plan is basically that purple box, right?
The one?
ROS plan is basically that purple box, the execution monitoring system.
No, in fact, ROS plan is the sort of task
gray
level
one,
handling
right?
executive.
The grey one, right? The big
Yeah,
one.
The big grey one, in fact, yeah.
Yeah, except that you plug in the task plan, right?
Yeah,
But
it's a
right,
task
Any
level.
plan that you want to use, yeah.
Yeah, so I mean, so there's different shades of it. So my group has been working on enterprise for a while. We've had a large number of people working with that as well. So we're providing that in this integrated environment. But there are different stages. So that's something that you can also plug in a new PDO planner into, right? But as if you look at the previous slide, there are different levels of that, right? Where you can open up what architecture you use, what task executive.
But so, for example, can I use ROS plan as the grey box?
Yes, yes.
Yeah.
That's my question. Okay.
Yeah.
Good.
Andrea?
So, because I have my own planning language, my own whatever, I can, let's say, locate my system wherever I want, but I just have to be compliant with the reference box, the interface with the system, and that's it.
Yeah, depending on how we design the tracks, there will be some limits, obviously, but if you're talking about this...
in any case, I have to be compliant with the actual interface, and then I can use whatever I want.
Yeah.
So this is just like a reference, right? It's not the only way to do things.
But so go back to your competition slide, right? I mean, so if you look at the community, there's a set of people who've been really working on the integrated robotic execution architectures, right? You want them to be able to have a competition, and something more like the freestyle makes the most sense in those cases where people have a system, right? There are other people who've been working on the planning component only, right? And that's track 1 or track 1A, which is just planning.
Yeah.
But the idea is to serve each of those needs. And if it's just people who've been doing planning and haven't been doing robotic execution, then you're not serving the execution. If you're just doing a freestyle, right, then you are serving the community, which is really important, but then you're not getting people who mainly focus on the planning and things like that.
And that's a particular benefit of the simulation. There you can just run hundreds of games. So that's what we, for example, also do for evaluation. If changes to our system actually make sense or improve things, we just leave it playing against itself for a week or against the older version for a week. And we get 100 games and then get a pretty good idea if that actually was an improvement or not. So, and then there's something similar that could be done that some of the games already run before the actual ICAPS, if that time is necessary, and then during ICAPS you only have the finals or something.
Tiago?
Yeah, so I think it was not created because in the second half of this we're going to have that gray box. We're going to provide the whole package of the simulation plus the planning and execution framework for design for enterprise. So we're providing the whole thing in the second half of this tutorial is going to be how that framework and designing strategy, complete system, everything. So that's why we're going to have to provide that whole system complete as a minimum, as we were saying, a minimum system. You can plug in ROS plan to replace the whole thing.
I assume the planning is done on a centralized machine, and the laptops and the robots are just for sensing and
actually, no, and that's what's currently the predominant strategy is really doing it distributed on the individual robots and then have a coordination step afterwards. So I'm not aware of a single RoboCup team at the moment who does centralized planning.
So, but our competition is going to be
in our
centralized.
competition, it's going to be the other way around. So there, it's more focused on the centralized aspect. to have a centralized planning system.
How many cores do we get to use?
Depends on how much.
How much money are you going to donate to the competition?
Well, so do I get to run a planner at home on my machines and send you packets over the network that say what the simulator should do? Or?
Such a gaming simulation.
Yeah.
Probably not, but we'll see. We are far from deciding on the finer points of the rules.
Okay. But it isn't about who can buy the biggest core, right? So
Just
so
wondering what kind of algorithms people are looking for here.
So the first year you would be able to do that if you had asked that question. So now
About the cores, if we do any tracks, some of them might be improved because it wouldn't be a fair
Sorry, can you
comparison.
say that again?
It wouldn't be a fair comparison, for example, if lots of the preprocessing has been done outside, and then you compare against a system that starts thinking as the competition starts.
Yeah.
So I'm just saying, there's nothing wrong with either way, but it's comparing apples and pears. So
You're right. We are aware.
otherwise it becomes heuristic search and that's what it is.
Yeah.
They will always be.
Okay, so that's just to sum up. The challenge here is an integrated planning and execution system for a medium complex domain in a similar robotics environment, which is inspired from industry. So I didn't go into much detail about this, but it's actually that talk to industry people, they're going from automation to autonomization of their production chains, and they're interested in this kind of scenario. That's also one of the pitches why, for example, Festoing is sponsoring this effort. And the tracks, so we talked about this in detail, and the timeline is that we presented the basic scenario last year, and now we have this tutorial and the discussion, and then we plan for having a first competition next year, after 2017 at that CB. Okay, now I hand over.
Yeah. So.
Can I ask a brief question about that last slide? So like, for instance, if you take the IPC 14, the competition was before ICAPS, but it was announced at ICAPS. So are you actually saying it's going to happen at ICAPS?
As I said before, it might be that part of it has to happen before, just for competition constraints or something.
Depending on how many competitors we get, right?
Yeah.
If we have 2 teams, we'll just run it at ICAPS.
Yeah. But the idea is to at least have something also running on site at ICAPS.
Okay.
All right. So, I first of all, let me apologize in advance. I'm giving a talk at the DMAC workshop in 15 minutes. But so I'll make this brief, and then I'll answer questions after the coffee break. So basically, I tried to come up with a few of the interesting challenges of this competition. So, first of all, right, if you're a planning guy, right, then this is what the world looks like to you, right? You've got an initial state and goal, you feed it to a planner, you get a plan, and you're happy, right? Now, you might actually be aware that there's this thing called an executive, right, that takes your plan and executes it in the real world, right? But as a matter of fact, right, there's this real world, right, which we sometimes like to call plan, for historical reasons, I guess, where the executive, right, dispatches an action, the action does something in the world, you know, gazebo simulation or on the robot or whatever, right? And then you get some information from the world, right, which goes through a state estimator. And the state estimator basically gives a state to the executive, and of course, what that state looks like exactly is not very clear, right? Or there's lots of options for what that state could look like. Right, and then the executive can be like, oh yes, the plan is proceeding according to plan, everything is good. Or it can be like, oh, what's going on? Replan, abort, do something. So here are some of the challenges related to each of these aspects for specifically for this domain. Okay. So first of all, Tim said that this is a medium complex domain. I would put it differently. I would say finding the actions that you need to perform for each order is easy, right? It's basically predefined. you have the exact steps that you need to do in the exact order. So that's easy. Now, you need to assign resources, right? So robots to the subtasks of each order, right? Which robot is going to go and get which base and put it there and so on, right? So if we go back here, right? So this is the plan skeleton, and that's basically known in advance depending on the complexity of the order. But who is going to execute each of these steps, right? Where these bases are going to come from, and sometimes the order you do things in, right? So that's not so easy. And if you add the time windows, right, then you go from a temporally simple problem to a temporally expressive problem, or to required concurrency. Right. So that's the planning challenge, right? Another challenge, which I kind of figured out when I was encoding this domain in PDDL, is that you need a ton of objects, right? So basically you need an object for each workpiece, right? So you've got 5 objects here with probably 4 different predicates, connecting them, 4 different types of predicates connecting them, right? And you've got some issues of symmetry, right? So, for example, all of the bases that are buffered in the base station are basically symmetric. So there is some, challenges just to planning, right, for this domain. Now, if you look at the planning and execution challenges, right, then you've got order is arriving on the fly, right? So you might want to replan whenever a new order arrives. You might want to anticipate some things. And then you've got, so I didn't write this down, right? You've got, no, actually that's the next one, sorry. And then you've got the fact that this is a competition, right? So what exactly is the objective here? Am I trying to maximize the number of points I accumulate? Or am I trying to score more than my opponent? Because those might not be the exact same objective. Okay? I don't know the answer. But, that's an interesting thing to look at. And then, of course, you've got, the fact that this is the real world, or maybe a simulation that tries to mimic the real world, right? So you've got actions that can fail. Yeah?
Your point brings up the question of do we have reliable state estimates on what the other team's robots are doing?
No. I'm being told no.
So we don't really know how much score they have.
How much score? You know. But I thought you meant how they are behaving. That you don't know?
So we do know their score.
You do know their score. You don't know what their score on.
But just their current score for us.
Yes.
Yeah.
You don't have any sensing data that gives you.
You might know the state of their machines.
You can do clustering based on the laser data that you get, but that will of course always be noisy. Yeah.
So the theory here is if they're way ahead of you, you might do a riskier action that has a higher chance of fail, and a last ditch attempt to win the competition.
Maybe.
If you can recognize the other robots and leave, then you could know what the plan. You could guess what kind of plan they are doing. Do they receive the same orders? Do both of them have the same orders?
Yes, they do.
So could you kind of like look at what the other person is doing, reason about that as well, or not really?
Yeah, but you're not seeing the
observations, right?
Yeah, you're not seeing the other robots most of the time, right?
But you said they have a sticker on the side, and
No, that's the machine.
No, that's the machine. That's not the other robot. So you can see some of the robots, but most of the time they will be somewhere else on the field, and
then you don't know what they're holding, right?
Yeah, and occluded by other machines or so, and you don't know what they're holding.
Right. So then on top of all of that, right, you've got actions have uncontrollable durations. Okay, so each of the operations on the production system machines has a lower bound and upper bound. Robots traveling has an uncontrollable duration that we don't even know how to set bounds on, or at least not very well. And then machines will fail. That's part of the competition. So for what, a minute?
Yeah, 30 seconds to 2 minutes. 2 machines. Yeah. There will be 2 events where the machine will be unavailable, so that you cannot. So we have to reschedule and do something else in the meantime.
Right. So Maybe action selection is easy here, but everything else becomes more and more difficult. So I will now leave you and come back for the coffee break, and I will take any questions you have then. And then Tim will show you how to run the simulation.
We know we get to the practical part, so maybe Tiago or so you can help out.
I can just pass this around.
So you can just take out a USB stick, then what numbers, and write down the name and email address, so we need to get them back afterwards.
If you have a laptop, but you can do it from these.
Papers for each one of a few systems there, but this gives you the kind of the overall kind of blocks that we have there. So on top, we're sending missions, and you can think as a PDL kind of goal specification. Robot B at a certain location, have order done at a certain time. So we have mission goals, and then Erez is going to present to you how you can send these goals to enterprise. On top, we have an activity planner. In this case, we're going to be playing around. You can plug in, plug out your PDL planner. Right now, for this demo, we're using PopTech. You can use Object, you name it. So with that, we have a timestamp plan that we turn into a temporal plan network. So that's what generates, that's generated from the plan. You can think about turning the PDL-like plan into kind of a task network. So pipe there, our execution monitoring system will execute, dispatch that action at a particular time or the exact time that you planned for, and it's going to monitor the execution by checking the state of the board, if the precondition is met, and if you're missing a deadline, and all that. So that's pipe over there. So this is what we call a goal-directed executive. That's where the most high-level planning takes place. We have a model, so that's how we specify PDL. We do the domain and problem file. Predicate estimator is what we get from for example, from the simulator, what's going on, right? So we can try to parse the continuous data, like the position of the robot, into something like robot at a particular region. So we're trying to discretize. So we can think about trying to map raw data into predicates, right, or functions. Can you say something?
No.
Sorry. So you can think about, when you send a mission goal, what's happening there is that we are all the time looking at the plant, right? And we're parsing that into a set of predicates or functions. So by the moment you want to have something done, that top part is executive will translate that into a PDL problem, or depending on the specification, use a PDL problem in this case. And they will give the domain and the problem to the planner, and then we go down for execution. Okay? So on the bottom part here, you can think about sending commands for each particular robot. In this case, you guys saw 3 robots, right? And you have the machines as well. So imagine that as being one of these big blocks being a robot or an agent, right? Each agent or each robot, you can kind of implement their behaviors. Like they navigate, they pick up one of the bays. So you can implement that as separate modules, right? So, and then this activity manager will say, okay, I'm receiving a command to navigate. It first detects which robot that belongs to. And then the second thing, in the manager will tell, okay, I'm going to execute a move. It knows how to identify what is the module that is responsible for executing that particular action. Right? So all this is on the raw, so you can imagine it's kind of message passaging, and action being, waiting for the action to complete, and then you're done, and you move to the next one. So this is how we implement different behaviors. In that case, we have a few, right? And then we can discuss about that. So if something goes wrong, all these modules are trying to accomplish this particular task. If something goes wrong, this manager here tells the executive, say something went wrong, I'm delayed, or I couldn't meet the precondition, or I couldn't finish this job. So the top bar would replan and try to reshape it based on what's given. So again, you can think about one particular executive on the top, and then every robot knows how to implement its own behavior. This is basically what we're providing, and we could potentially have a track that you just play around with the planner and the domain, That's what we put it out, put it in, try different things. Or, as we're saying, you can just remove all of this and try Rob's plan. That's something totally different executive to playing around with the simulator. Any questions about this, before I move in and we start playing around with the demo?
Does everyone know who Pike is?
Yeah, it's not completely clear to me what do you mean by failure. So what is going to tell you that?
Yeah. So who's going to tell you? Or what's
the fact? So it is going to tell you that state, so that predicate doesn't hold, for instance, and then it's the goal-directed executive that declares that the precondition is not satisfied.
Right.
Or there is a notion of failure, so the outcome of an action can be failure.
So that depends on how you model. But let me start with the monitor and the monitoring system.
Yeah.
So what that's doing is doing a causal link analysis, right? It's trying to say, okay, so these are all the preconditions I need. This is what I'm expecting at the end, and I have my whole plan, and I know what's going to be has to hold, at every point.
Yeah.
Right? So if something breaks in the middle, then I don't have to wait for the actions to be executed, so I can say, oh, it's going to fail at that time. So if I detect something before, I'm going to break way before, right? So just looking at the predicates and analyze, the causal link between all those actions, and I can detect.
So there is already some intelligence.
Yes. It will detect. If an action ends, if you have a time bound to finish or start your activity, right? And if that guy dispatched and say you have to execute now, and the action didn't start it or didn't finish at that time, it will detect it and say, stop. Something was wrong because we're time dependent. Let's say. So you can detect a few problems right there. Right? But you can also kind of start detecting problems from here down. Right? You can think about your own trying to execute lower level tasks and you're breaking there, right? And what you just have to say is, I failed, And then at the top part, the new state of the board will tell you at least what's going on, what the initial state.
The model of the action is always the same. The model of the action is always the same.
Yeah.
So cannot be wrong.
Yeah, you assume that it's not wrong. Yes. Okay. Yeah. But you can inject, if you can model you can put in your model certain variables that can help you out to say, we're in a failure mode right now, so we should recover. So if you have it explicit, that would help, right? Recovering. Any other questions about this? Yeah, it's a few blocks. It has kind of a, it puts robots to do their own things. You can put robots out in, if a robot breaks, it's fine, everything's going to still run. So just a quick comment, this is being used a lot in the lab, used for controlling aircrafts, underwater gliders, rover scenarios. We have a few demos tomorrow, not only about this, but other applications of enterprise. We applied this in a course. They had to control a robot, a Max 1 robot, around a maze, different tasks. So we use that just as a platform, and they kind of build up, create their own behaviors and all that, and manufacturing as well. So I know it's very high level, but imagine there's something there that will take care of of planning, and it's kind of what you have to do is just set goals, and that will be it just for the start. Okay, so Eric's going to give you a little bit of how enterprise is now going to put the two things together to show you how you can run it.
So do you have references for all the papers that explain this somewhere?
We do have for the components, right?
Yeah.
So that we can put it either on the Google group, or we can put it there. Yeah, at the end.
So if you want to, understand how Pike works in more detail, then there's paper too.
So we do have a planner called Kirk. We do have the existing Pike. That's what we're providing today. So we do have a Pike. Sorry. So there is a path planning. It's a risk-aware path planning that we also have in our group. That's Sulu. So that navigator right there. We can put all the references in that, but today what we're going to be showing, like running, is a pop path on the activity planner, And Pike, that's the one you're going to be kind of monitoring and dispatching the activities. The navigation part is actually being taken care of the ROS package. I think is the ROS move base that what's being used. Which one is the navigation stack?
That's inside Fox. That's
right. Yeah.
Yeah.
Yeah. So, but there is within enterprise we implement something that calls the local planner or the global planner.
It's basically a robot behavior that you can call.
Yeah, you can
go to the input side of machine X.
Yeah. All right. So I would pass it to Eric. I don't think you need this.
Okay. So all of the code provided by us is not on the stick right now, and the reason for that is our code hasn't been really open sourced yet. So we need you to, if you want to run this on your machine before the competition, we'll need you to just accept like a research use license. And Tiago, where's the link for that again?
Yeah, so that's on our website. And if you go on the bottom, you will see enterprise license. Click that, and you'll just click, policy, whatever terms.
Don't read it, just click accept.
Yes. Just say agree, and no, so on the bottom, just put a few information if you can, but just say agree, and you're going to get a pilot key for that.
Yeah, and then give MIT the keys to your house because now we don't exist.
Yes.
And I will say that my personal goal is, and I'll be fighting for making sure that by the time the competition kicks off, we have the framework that we're going to give you open source, because that would be ridiculous if it wasn't.
Yes.
So if you fill out that form and follow the instructions afterwards, you can then get our code on your computer by running this SimStick update script twice. For some reason, Catkin didn't quite work the first time, so just run it twice, everything will be happy. Then start the simulation like normal. And actually this one, if you follow these instructions, you'll get 3 robots running.
Do you want a flash drive to run this?
And then, okay.
So take one at a time, but you have to give it that afterwards. 24. You boot from this. So you just boot from this and you get Fedora. Is it going to go okay? There were some issues with Macs.
Yeah, it did boot.
Yeah. But this looks like it's old enough. So it might not. We'll see. Yeah.
If you want to use, you can use this one.
Oh, yeah.
You want to try this out? You can also use that laptop. Okay. No, probably not. Yeah. Okay, now I'll take this back.
Erez, how do you get started? Like,
we need to tap twice sometimes on that.
Oh, there we go.
The number 2 twice
Anyone else want a flash drive?
Okay, cool. So we'll launch a simulator. And right now, included in this, we gave you very a pretty simple domain, PDDL domain, and problem model. enough to essentially show the system working and drive the robots around. So,
I don't know if I would call the PDD domain simple.
Okay, incomplete, so let's call it.
Yes. It is not complex enough, but it is not simple.
Yes.
No, it's not simplified, it's just not ready. But it's almost ready.
And then, so once you have the simulator running, you just run the command, where'd it go? Launch enterprise. There's still some debugging cruft in here that'll get updated. And
so what Eric is doing now is basically adding the team to the simulation through the referee box.
yeah.
And that adds the machines to the playing field at random locations.
Do you want to refresh the page?
I'm going to wait until this actually finishes loading.
Can you show the TTN that you're going to run? Do you have the TTN here?
There we go, okay. It's not on here right now, but
Okay.
I can show it. So we also have, so in order to just play around with this and start kind of figuring things out, we have a web-based interface for you to be able to see all of the predicates that are true, and for you to add your own if you just want to mess around with things. And we can also set goals here. So let's say that I want robot 1 to be at ICAPS station 1, and I want robot 2 to be at Cyan base station. These are the yeah. We have this in here because that's close to what they're called in the simulation, so more descriptive names. And you can send this to each plan, and then you can see the robots going off and moving. So right now the model is sufficient for moving around, and when tasks are reported as completed, the predicates should update. Yep. So you can see now that robot 2 is at the base station, and 1 is getting a little lost. I don't know why it's getting lost, but sometimes it does. Great. And this isn't included in there right now, but we can in the next update. So this TPN viewer is what we parse the PDDL output. We parse the PDDL output into a TPN, temporal plan network, and this is essentially what Pipe is executing. Is in parallel, it's moving robot 1 to CS1 and robot 2 to BS. And because we didn't go through the effort in this to model times appropriately, we just have huge time windows.
So modeling durations of these actions is one of the first challenges here, right? Because PDDL doesn't allow you to specify uncontrollable durations.
Somebody, I forgot the authors modified, they had an extension of it last year.
Yeah, it's not hard to modify, but then you need everything to support that, right? But yeah.
So included in here for the competition version will also be a place for you to drop in a path planner if you want. We'll provide something simple, probably even just this, and use it to get rough time estimates, but you can probably always do better than the basic stuff we'll give you. Chip, why is this robot getting
I was
lost?
looking for a way for the machines, but they're heavy placed in this iteration.
Move them. You can move them in gazebo. I think you have to click the move thing at the top toolbar.
Right. There you go.
Research here.
See how easy it is?
Oh, it's right there. Wow.
Now, do the robots get the updated ground truth?
I don't know.
They have the ground truth.
Do they?
What?
Do they? Do they? Yeah.
So you need to get the other one.
So the robot won't know anymore where the machine is, because then it only does once, and then the assumption that it's not moving. But the robot obviously knows where it is, because for self-composition and so on, it doesn't recognize or does not do it.
So anyways, this is a preview of the system that we'll be giving you for the baseline execution capabilities. Like I said, a visual HTML interface to just kind of poke around and experiment with things. Visualizer for the plan that's being executed, and the actual capability to execute that plan, and signal failures when they happen. And I think that's about it.
So just to be clear, right? This is enterprise. This is one of your options, right? It's not the only one. It's probably the one that's going to be best supported, just because half of the organizing team of the challenge is working on this, and I used to. But we will try to accommodate basically anything that you want to do, right? So if you want to use ROSPlan, then we will help you do that. If you have some other system that you want to use, we will help you do that.
Right? Planner, execution system,
Yeah.
estimator.
Okay. Is there anything else you want to show them?
No.
Okay. So basically, this is the part I was looking forward to the most, right? The discussion. So we want to hear from you. We already did in the beginning, right? But am I standing too close to the camera?
No.
Just wondering whether to turn it off or
All right.
leave it on.
No, leave it on. Leave it on. I won't remember any of this, so it's good to have it recorded. So basically, we want to hear from you kind of initial thoughts, right? So first of all, whether you actually want to, participate, what it is you're thinking that you want to do, right? So what components you want to replace or modify, what components you just want to use and not worry about, what are the tracks you would be interested in participating in or not, and you can, feel free to invent tracks, right? Because we haven't, decided on any official rules yet, right? So I guess the people that stuck in here at this hour are probably the hardcore of the people who wanna participate. So yeah, basically anything anyone wants to say.
So let me start. So Chris Beck again, I think I mentioned that before, just want to say it again. So Chris Beck told me that for his group, so for maybe for scaling people, it would be nice if we can have somehow, if we have the distribution of how the requests are coming, that's a potential like door for their group or his group, and then any scheduling and or people that will be good for them.
A little bit louder.
Sorry?
Could you speak?
Yeah, sorry. So what Chris Beck said was it would be nice. His concern was that if we use the simulator as it is right now, just kind of randomly kicking order requests, right? For him, it would be more interesting for the planning committee, the scheduling committee, to have as input, you give the distribution of how those orders are coming, in behind. So that would be more like, yes, more people to say, okay, so we can play around with that, we have this vision, how we can anticipate any arrival on order at a certain time, so we can be prepared for that.
That's reasonable. So that can be done because there is a bias in the generation of the orders anyway. So we generate a specific complexity set of orders, so that's fixed. And there are certain time constraints that we have. For example, as I said before, complex orders can only come later in the game, so that the lead time is long enough. So from that follows a certain distribution over the game that we have. And then there's even slightly more bias because in the code that generates these orders, there are minimum and maximum time ranges in which we expect the orders to come. It's just from running at RoboCup and testing out what teams could accommodate, it's in there. So, and that could be something that could be varied a little more, but then announced, for example, to the teams. And from that we can infer that kind of distribution. So it's a sparse distribution because there are only a few orders, but I think it can be done.
So you know the distribution of orders and you can anticipate them and you can possibly do something clever. Now, let me also just add, right, kind of, what I think would be the ideal outcome from, this endeavor is, so fine, we'll have a competition maybe for a few years, and then once we've kind of feeling comfortable with this, we can field, an ICAPS team for the RoboCup Logistics League challenge and kick all the roboticists' asses, because we'll actually have planning. So yeah, that's...
Do you have a conjecture that that's what would kick all the roboticists' asses?
Yeah, what's the evidence that
Like
that's
I don't have any evidence, but considering that what they do now is basically write rules.
But I mean, the domain might be simple enough where planning is just not really required.
It might be. I don't think it is, because it's a really, really hard problem. I mean, even if you knew everything in advance, it's still a very hard scheduling and resource allocation problem to do it optimally, right?
George Niemueller, did crew scheduling for Delta, and after working on it for a year, he was able to remove one crew from their global schedule.
Yeah.
Meaning they were incredibly close to optimal having done it manually.
That might be
very
the case.
hard problem, but
yes.
It didn't require...
That's true. That might be the case. So, hopefully we'll know in a year, right? Yeah.
Just to be antagonistic
please.
for a couple more minutes. So one reason to want to participate in this is that if one were to do well, someone might care.
Yes.
But when I go to the RoboCup Logistics League website, I notice that it lists 3 teams.
That's outdated. So this year alone, I think we have 4 new teams coming up. But these are also 3 of those teams switching for other RoboCup leagues there. Because they also are more on the AI and reasoning side, and they said, oh, finally it's something where we have a good balance between the two. So this year there should be 8 teams participating from, I think, 4 or 5 countries or so. So it's increasing. And also most of the teams have some industrial sponsoring in the meantime. So I think this is growing, especially this year. We have established the RoboCup Industrial Umbrella League, which fosters cooperation also with RoboCup at work. And so that might also give some more momentum to make this bigger and more interesting.
I think you may wanted to have something.
Yes, so would you be able to call it the best performance so far from the competition as a benchmark so that we try with it? So that if you want to show that you come close and beating them.
If you run the Asian right now, that's the Asian that won the last 2 competitions, or the last 4 competitions. Okay. So the last 2 years.
And I remember in the earlier part of the talk, you mentioned that the objective of the different track is still not clearly defined yet.
Yeah. I mean, so we don't have any rules yet, right? So first of all, right, there's different ways to run the competition, regardless of the tracks, right? But you can compete on kind of total score, right? So we can have, pairwise matches and who gets, the most score or total. Or you can have kind of an elimination thing, right, where you're competing against someone else, and then the winner, advances to the next round.
So why don't we follow the same thing that they have been using before?
So we're doing a round robin where total points count, and then the best 4 or 5 teams advance into the playoffs and finals, and the playoffs is still round robin, and the finals is obviously elimination. So, but in the playoffs, it's no longer the total amount of points, but the game's won. It's more like soccer, where when you win a game, you get 3 points, when you lose 0, and if it's a draw, each team gets 1 point.
So is there any reason that we don't employ
No, we can use that.
No, we could.
Make it simple?
Yeah, that sounds reasonable to me. I mean,
instead of having another power to think about
I mean, so even if we use that, right, then that means you want to behave differently in different phases of the competition, right?
Yeah.
Yeah, I think that's interesting. We might actually simplify that, but we might not. I think we'll probably keep that for the rules.
So that has worked well so far. We thought sometimes about changing it, especially the playoffs could be a little bit more like the esports leagues are doing it, but these are minor details.
Yeah, my only question was, you wanted to kick the roboticists' butts. That's only going to work as well as the simulation, right?
Yes.
So, I mean, I can imagine doing excellently on the simulation, going to the real robots and failing miserably.
So
because the simulation made a bunch of assumptions, or, I mean...
From past competitions, so the team winning the last 2 years made the simulation. So, and they always go first for simulation, and only then after some time go for the reroll. So that actually works fairly well, because assuming that you get the groundwork done properly. So you have the machine handling in place, and that works reasonably. That's obviously also a showstopper if you don't get that right. But then after that, the simulation and the reroll is not that much of a difference.
Also assuming there's no carpet.
There's no garage.
Yeah, I mean, that's the life of
There's
robotics.
sunshine coming in.
Yeah.
You always train with that sunshine.
Yes.
That's the
I mean,
or rain. Sorry.
No, so another good outcome would be, a collaboration between each of the teams here, right, and a robotics team. Right, that would be maybe even a better outcome.
So the teams are really spread across, with a slight concentration in Europe at the moment. But I think there are opportunities for cooperation between teams, because there are also some teams which come from a more industrial background, from mechanical engineering, and they have a hard time getting this decision component right.
Yeah, they like to write differential equations.
Yeah, but they get the control right, and they get the hardware right. So there is, I think, potential to group up.
So in the contest here, is it going to be sort of NASCAR-like, and everybody has the same sensors, everybody has the same robots? That's what yes. So you're not talking about coming in and the team supplies their own sensors to get better resolution?
No.
You're talking about the simulation, or you're talking about RoboCup?
Our thing.
Our thing.
Okay.
Yes. Yes.
Okay.
Yeah, right.
Yeah, I guess another question, I guess following up on the idea of the real versus simulation, because I know a lot of the RoboCup competitions, usually they send out the robots and it's more of a decentralized thing. Every robot has its own system, but from looking at the enterprise and the system, it looks like it's very centralized here.
Yes.
So I guess I wasn't sure, maybe is the logistics competition itself always centralized, or will this be an issue to consider as a jump?
What we're going to run is a centralized competition.
Okay.
So we're not going to, we're going to let you do it in a centralized manner. If you feel like, doing it distributed, we're not going to get in your way, right?
Right, I wasn't meaning it for that.
Yeah.
I was thinking because you were saying that we could go and maybe compete in the real RoboCup, but if they're doing that with decentralized, then that might change a lot of the methods.
So let's, not put the
right, sorry,
for the...
I didn't mean to cause...
Yeah, no, you're right. I mean, you're right. That's somewhere that we want to get to.
But the logistics, but the logistics in RoboCup, there is the explicit statement that allows you could bring your own cluster, as long as it fits a regular, 16 amp car socket or something.
Okay.
So that's essentially the constraint that we have. And so you do not need to do all the computation on the robot, and that's an exception in RoboCup rather than the norm. You're allowed to have off-board computing.
Oh, okay.
The risk then there always is you have to have methods in place to deal with the shitty Wi-Fi in RoboCup. But that can be overcome. So, as we're doing. So also, when we have 3 robots, we do have a synchronized robot model. So we have leader election, there's one master robot elected, that could also be a station on the side, but currently it's just not. And then that collects all the information from the robots and then distributes it back after it merged it. So, and that could be the exact same stage when you start applying your simple plan.
All right, thank you.
So, would anyone be interested in looking at the PDDL model we have now and kind of seeing how ugly it is?
Yeah.
Yeah, it's ugly.
I see a note there.
All right, let me pull it up here for a second. If there's any more questions.
I think just for this one.
When are you going to make the decision about whether to move ahead?
So we're definitely going to move ahead. We're just not sure about exactly how. But so we wanted to wait for feedback from the community to see what people are interested in doing. So basically we have the mailing list that some of you have already signed up for. We're going to send out a questionnaire in a few days, kind of asking you what you think you're going to want to do, what you're going to want us to provide, what type of tracks you'll be interested in, whether you would be interested in working with real robots if that was an option, all sorts of questions like that. And then when we get the responses, we can decide on the tracks that we'll have more than 2 people in it, or more than 1 person.
So just to change back, if you're interested, RoboCup is in 2 weeks, starting on June 27th or 28th. So, and it's this year in Leipzig, Germany. So if you happen to be around, I think it's a good opportunity. Next time it's going to be in Japan next year.
So when you say RoboCups, they're normally over there, there's multiple RoboCup competitions?
There's one RoboCup competition per year. So one real large RoboCup, and then there are some open tournaments which are regional. So like the German Open, European Open, Dutch Open, or Japan Open. And the main competition, which comprises soccer at home, rescue, and the industrial leagues, is by the end of this month until July 3rd. So I think the finals are on July 3rd, and that's usually pretty cool.
And logistics is one part of that competition?
Yeah, it's so it's organized in different leagues, and the logistics league is one particular league, and then there's a rescue league for rescue applications, where robots have to drive through disaster area, and there's many different soccer leagues, humanoids, wheeled robots, larger humanoids, custom-built humanoids.
So I remember, like, at least for robot software, that they changed the platform a couple times already, right? So for logistic leader, they will stay with this platform for some time in the future, and then the composition of the team, 6 robots, things like that, will be stable for a while.
Yeah, so this robot was introduced last year, so it's a new version. The version that they had before, they had for 4 to 5 years or so. And I would guess this will stay for another couple of years. So there's currently no new version anywhere on the horizon.
Right, and the composition is 6 robots, that will stay for some time.
I guess so, yeah.
Because I think that one thing that planning is good at is kind of do very independent, which we can add another robot in, or add another task and use software and adapt to that quickly. So
that's true.
Actually, if they change that frequently, it's actually playing.
That's an interesting point, yeah. So maybe we can.
Yeah, that's something that we can easily accommodate in simulation, right? So we can just put in robots, drop out robots. We can also give robots an energy level so that they actually need to recharge for some time or so. So So that's something that can do much more easily in simulation than in the real game. But there you have to care about what's the hardware interface, what's the cost, and so on.
So just to kind of quickly go over the PDDL domain model, right? So you've got a team, you've got a robot, you've got the machines, and the different types of machines. The machine has sides, right? Input or output sides. There's magazines and delivery slides. You've got the workpieces with the subtypes, colors, orders. You've got a bunch of constants. Right? So basically, these are the teams, the sides. You've got the stations. You've got. If I showed you the initial. So basically, you have something that generates hundreds of objects in case you're going to need them. Right? That's one of the challenges here. Then you've got a bunch of predicates that determine right which ring station has which color, whether there's a cap in the slide over there, right, whether the slide is clear, how many bases you need for each type of color, how many bases are loaded in a ring station, whether something is on the shelf or not. This is basically block world for the workpieces, robot positions and gripper, orders, some other stuff for the slides. So your actions are, right, the robot can move to a machine, can place a workpiece in the machine, right, either input side or output side, and you can pick up a workpiece from the machine. You can place the workpiece in the machine shelf, right, you need that for the caps, and pick up a workpiece from the machine shelf. You can replenish a cap station shelf. That's basically like a virtual action, but we need that, right? So in the real competition, you've got a person coming in and replenishing the thing, but this is just a virtual action here.
As for buffering on the cap station, because then the shelf will initially be filled with bases and caps, and once they're gone, you're allowed to refill.
And then you can dispense a base workpiece from a base station. You can so this is kind of for managing orders. This is kind of messy, but. This is how you say that this workpiece is going to fulfill this order. Okay. You can deliver a workpiece once it's loaded on the delivery station. You can load a cap into the slide, and you can place a cap on a workpiece. So this is something that tells the machine to do that. Place a ring on a workpiece, tells the ring station to do that. Load additional base to workstation. That's loading raw material, and that's it. Right. So. This is not a super complex domain, but it's not trivial.
With the basics.
Yeah. So we will, debug this a bit more and release it. Of course, you're also free to modify the domain model, right? If you do that, you might have to, kind of worry about action names and making sure that they're dispatched correctly, but that's not a big issue. Yeah.
So let's quickly look at the description. There are two things. One is that it seems that the number of parameters are really large.
Yes.
And that's one thing that blow up the routing process.
So a lot of those are actually statically determined. We just need that, right? So for example, if you look at a move to machine, right? So you've got robot moving from machine, that's determined by the current state, and from side, right? That's also determined by the current state, and it's moving to machine and to side, right? So that's really just one position. It's just split up. And then the team makes sure that you're moving to a machine that your team owns. So that's also statically determined. So it's really just a standard move to, right? Even though it looks like it has 6 parameters, it really has 2. And I mean, it's the same, right? So all of these actions have team, and you've got the machine and machine side, which is really one thing, right? It's your navigation graph. And you've got your robot and a workpiece. So it's not, I've seen much worse.
Okay.
I've seen, actions with less parameters.
So right there, I think we can reduce at least in half. Like you can put team as a bracket. You can put, if you have just 2 sides, you can put as a constant. And you've already got 3 out of it. So
Yes, the other thing is like, it seems that only one action has duration of 10 and all the other have.
Oh, the durations are meaningless. We didn't actually do the durations yet.
Okay.
What, did one of them say 10? That was just a typo. They're all supposed to be 1.
Oh, it's supposed to be 1, not 10.
Oh, no, yeah, maybe I said movement is expensive and everything else is cheap. I don't know. Yeah.
So, will the domain description and some comments be available?
The domain will be available. I don't know if some problems will be available or whether it will just give you kind of an interface for the simulator to generate the current problem.
Because it would really be interesting just to have it, to see what, how long it took to generate plans for just, simple problems.
Yes. So this, I can tell you that this varies significantly depending on the time that you use.
Yeah.
Yeah. So let me see if I can. I think I have this here.
You should open this up in the editor.
Which editor?
Editor.tiny.net.
Oh, yeah. No, you're right.
Seriously,
Wow.
I'll open in the editor, I'm telling you. Just don't use Internet Explorer.
We're almost there, halfway.
Domain or domains?
Domains.
Can you
Nice.
just this pipe and plug in of yours?
Yeah.
And then
And that part is flat, so it's probably going to be that for the next one. I know, yes.
Alright, so I wrote something that kind of generates a large enough number of spare work pieces. So this is, I think, what the...
Like, is this, you said there's only going to be so many orders at the time. Is this really a better model than using clay objects? Just with the maximum number, then once you've done...
This is basically what we have. These are I didn't do this very efficiently, right? That's something you guys can work on. But so a lot of these are basically kind of caps that are off in the middle of nowhere, and you can use them to replenish, the cap station, for example. So they're all symmetric, except they have.
Well, that's what I mean. If you know you never need more than 5 caps in the game at one point.
Yeah.
In time,
So
once you're done.
So that's what you get when you replace 5 with I think 20. You get 600 objects plus. A bunch more.
This is non-engineering, by the way, we're talking about that, right?
Yeah. So, this is one of the challenges for the planning side here, right? How do you make this more efficient? Because this will kill you if you're trying to ground things. But at least the domain is nice and compact. Sort of.
What to run it?
No.
Run it?
It's temporal.
Oh, right.
What, with the 10-second time limits? They won't even finish reading the file.
I'll never know. They're saving us in. Sorry.
No, also, in this problem, the goal is already achieved in the initial state.
See?
Because, right, so you basically got your orders. Your goal is to fill the orders, but before the orders come in, they're filled. Right? So, because you also need to generate objects for orders on the fly. So what we do is just have enough orders, and we assume they're filled until we get the actual order, which triggers a replan. Hey, your goal became false. But even just reading the thing and checking that the initial state satisfies the goal is not trivial.
How long does it take to translate into SAS?
I haven't tried. No, so this is derivative. This is derivative, and fast downward doesn't read derivative PDL. And I think temporal fast downward actually does fairly well with this. So with the smaller instances that I've tried, temporal fast downward worked really well. I'm giving you a hint. Now other planners also worked.
But
some didn't.
But certainly, I've seen the fast downward parser just die if you have too many objects. The iterative one doesn't do that, or?
Oh, I didn't try the tempo fast with the 600 objects. I tried it with one.
My guess is that generating the grounded SAS file is going to just.
That is very likely.
So a lot of temporal domains do not have any interest in temporal limits. So it's one of those domains where we could just throw away time, solve it with classical planner, and then insert the
If
schedule.
you didn't have the time windows for the orders, then yes. But because you have time windows, right? So you need to finish, this order in between, 5 and 10 minutes from now. Then it becomes temporally expressive, temporally interesting.
Yeah.
Okay. Yeah. So so inherently it's not. If you don't have the deadlines, temporally simple. Just find a sequence of action, schedule it, you're fine. But yeah.
Can I request that there be a how-to about how to download the software and how to run a complete competition with 2 teams competing with each other in Gazebo?
I'll put up the links, we have that.
You have that already?
Yeah.
Where?
It's on the Track wiki site. And if you go to index and then look for GutSim setup 2015, that's essentially what you all need to do to get the simulation set up on your own system.
But we need to update that with instructions on how to run, enterprise,
Yes.
for example.
Yeah, that's for the existing agent system.
But yeah, so basically,
If you get that far, that's already a large part of the way.
Yeah, so our goal is to make this as painless as possible. It's not possible to make this completely painless, because we still have to deal with simulated robots. But we're going to try to make your lives as easy as possible. All right. So if there are no more questions, comments, criticisms, all good. Then I think we can wrap up here, and let me remind you that we're meeting, I think, at 6:45 to walk to the London Eye, right, for the opening reception.
Where are we supposed to meet out in that lobby area?
Here.
I think so. King's Building, main lobby, I think that's where the registration was.
Yeah.
Yeah. So we're gonna basically have a demo during the demo sessions, just showing this. Hopefully, getting more people to join the. I prefer calling it a challenge, not a competition. I think it's more friendly.
Thank you, guys.
Thank you.
Thank you.